right, so let's take a quick look. We'll build in some time for you guys to get questions answered too, but I want to at least introduce the idea of logarithmic differentiation. Okay, so this is stuff we've already been doing, right? We're just practicing our rules here. The point I want to make with this one is just that these are both essentially the same derivative rule. So what's the answer to this? Whether you have absolute values inside the log or not, works the same. Yeah, so we're going to get the derivative of hand, which is derivative of sine, so cosine x over sine x, and what is that equal to? Cotangent. So there's our answer. Okay? Okay?
Wait, that's the actual answer.
That's it.
Whoa.
Mm-hmm. Mm-hmm. Right? Because the derivative of log u is just u prime over u. Okay? All right, what about something like that? Okay, now just a quick review. If we wanted to do this derivative, we would always want to take advantage of the properties of logs before we differentiate, right? So we would rewrite the argument of this. Well, we would rewrite this logarithmic statement, rewrite y as log 7 plus the log of cosine squared, which would be 2 log cosine. Right, and now the derivative becomes much easier. What's y prime? Okay, well, oops, oh. Oh, I don't know what's going on here. Well, okay, never mind. I'm not going to change that. So what's the derivative of log 7?
7.
No. 0. How come? And because isn't log 7 just a number? Right?
Yeah.
So the derivative of a number, derivative of a constant is 0. So we get 0 plus 2 times the log. What's the derivative of log cosine? So we get our 2. Yes, times negative sine x over. Right, so we get negative 2 tangent x. Yep. Okay, give me thumbs. How we doing? Is that all good? Okay. All right, so then logarithmic differentiation. So there are no logs here, right? There's no logs. So why would we use logs? Well, look at this horrible. We've done problems like this, right? And it took us boards and boards of work to do these. Because this is complicated. Look, I've got a quotient, so I got to use quotient rule. But what does that involve? Well, the denominator is 2 layers. That's chain rule stuff, right? I've got a square root of a polynomial. On the top, I've got a product and a chain rule in the product rule. That's a mess, right? Wouldn't it be nice if there were a better way to do this?
Yes.
There is. Okay, logarithmic differentiation. So anytime you have an expression, you have a function that involves a tangle of products, quotients, and exponentials only, right? There's no addition or subtraction outside of individual factors. Then that leaves room to leverage the properties of logarithms. Think what properties of logarithms did. They moved us down the PEMDAS chain to make things easier, right? So I could do that here by just logging both sides of the equation, okay? So let's try this. Look what happens if I take the log of both sides. This is called logarithmic differentiation. So this is going to give me, this is really cool, and there's nothing new here. I mean, this really doesn't add anything that you guys don't already know how to do. It just combines some skills that we've been working on into a technique that's very useful. Go ahead. Well, no, but it's an equation. As long as I do treat both sides equally, I could take the log of both sides and then it would still be equal, right? You don't multiply, you take the log of both sides, right? So the log of y would then equal the log of that mess. Okay, but look, the log of that mess can be made much, much easier. Yes?
When you're logging those sides, is there ever like one that you always pick? Or like why wouldn't you pick log 10 over natural log?
It wouldn't make any difference. It would all work the same. Yeah. Would all work the same. Whichever base you're using, the properties of logs all work the same. Okay, so like as an example, it's a good question. So as an example, we wrote the properties of logs this way, right? Like I said something like the log of a times b equals log a plus log b. I could just as easily have said the log log of ab equals log a plus log b. Or I could have put a base 7 on that if I wanted to. Still going to work the same. I just have whatever log I'm starting with, I'm taking whatever log I'm using to take the log of a product, that appears in the other logs also, right? Okay, make sense? Uh, maybe I'll throw this in now. We'll talk about it later. But you can also convert between logs pretty easily, right? Like if I want to know what the base 3 log of 27 is, just kind of a calculator issue I want to show you. You can use the change of base theorem here. So I can rewrite this as any base I want, like I'll do natural log, the natural log of the argument divided by the natural log of the base. And those are keyboard log functions on any calculator or Desmos or whatever. There's not going to be a key for the log 3 base of something. Nobody ever uses that, right? We use base 10 log and we use base E log primarily. But I can always take any base log I want to and find its value using technology by just breaking it up that way. Okay, make sense? Okay, so back to business. Yeah, absolutely. You could, right? I mean, there'd be no need to because natural log is a keystroke log, but you could. We could say the base E log of 5 equals the base 10 log of 5 over the base 10 log of E. That's true. Okay? Make sense? Yep. Okay, back to business though. What about this guy? Okay, so now we took the log of both sides. How come? Well, look at that. What can I do to the right side using my properties of logs? Yeah, okay, so you guys are good at that. We've had a lot of practice. You had an assignment on that stuff. You're awesome at it. What's that going to be? Okay, log x plus log of that, but I can take the exponent out front, right? Right? Easy. Okay, now I can find y prime. The only downside of this, and it's a very small downside, is when I find y prime, I have to use implicit differentiation instead of explicit differentiation, right? Now, if we had just charged into this is an explicit equation. It's solved for y. So I would have gotten y prime equals an enormous mess, right? Not worth it. Down here, I have to implicitly differentiate with respect to x because the y is locked up inside a log function. It's not isolated. No big deal, though. What's the derivative of log y with respect to x? Y prime over y. Exactly. Isn't it? Right? So the step I'm taking here to go from this row down to this row is implicitly differentiating with respect to x. Okay? And this gives me y prime over y. Everybody give me thumbs on that. Does that make sense? Okay, we take the derivative of what's inside the log divided by what's inside the log. Okay, equals, these are all easy. What's the derivative of log x? 1 over x. What's the derivative of log x plus 1? Well, we'll multiply by 3/2, but what's the derivative of log x minus 1? What is it? Exactly, times 3/2 is just 3 over 2 times x minus 1, right? Minus, isn't that just going to be 1 over 2 times x plus 1? How easy was that, right? So then if we solve for y prime, we just get y prime equals all that stuff times y, right? Okay. So okay, let me see if I can be tricky here. I seldom am able to make, oh, of course not. How does that not work? Okay. Plan B. It's all times y, right? Okay, so all that stuff is times y. But what is y equal to? Y just equals that, right? Okay, but big deal. I'm not having to differentiate it. I'm just multiplying by that. Big deal. I just have to write it down. It's not hard to do, right? So here's y. So let's plug this in. Right? And what's that give us? Well, it was, we can see what it was. It was x times x minus 1 divided by square root x plus 1. There's my answer. Done. That's pretty cool, right? That made that so much easier. That would have been a lot of work if we hadn't used logarithmic differentiation there. Okay. Again, do you see why we were able to? It worked because the function that y, that defined y was a combination of products, quotients, and powers. Okay. What about one like that? Can we use logarithmic differentiation there? The answer is no. And how come? Yeah, this is why. The answer is no because of that. Because remember our properties of logs, what we said. The properties of logs, what they do is they move stuff down the ladder, right? Exponentiation moves down to multiplication. Division moves down to subtraction. Multiplication moves down to addition, but there's nowhere for addition or subtraction to go, right? So if you're starting with addition or subtraction, you're stuck because the properties of logs can't be applied. There is no property of this log. The log should do natural log, huh? I've been doing natural log. natural log of a plus b has nowhere to go. There's no property, right? Or minus. So that's what messes us up, okay? How about that one? You have no way to do this. There's no, I mean, no, you can. You're right. You can do it. You can apply properties of or logarithmic differentiation. Without it, you can't do this problem because there is no derivative rule for a function to a function power, right? We don't have it. We never will. You have to use logarithmic differentiation here. So what would you do? I don't multiply by log. I take the log of both sides. So log y equals, what would the log of the right side be?
Log x.
Well, I can pull the 2x down out front, right? There you go. Okay, and so implicitly differentiating is going to give me what? Yeah. Y prime over y equals, okay, now the right side, I got to differentiate the right side. No.
2 times
Mm-mm.
2 times x times 1 over x.
How are you get, well, no. Because you only had one term there, right?
2 plus. No.
Okay, differentiation, and again, please don't throw stuff at me, but differentiation is easy because you just follow the rules. You're getting close to, what's the rule? You're still not quite to that place yet where the rules are so, you know them so well that it's easy, but it's coming soon, I promise. What's the rule you have to follow to differentiate the right side? It's a product, right? You get that now? I mean, those are the patterns you're looking for, right? If I have an expression that is a product of factors, then I have to use the product rule when I differentiate. So we would probably just group, rather than factor the 2 out, let's just group the 2 with the x, okay? So what's product rule tell me? Times 1 over x, okay, so there's my derivative, right? Plus, whoops. Yeah, plus 2 log x, okay, which just becomes 2x over x is just 2, right? So y prime over y equals 2 plus 2 log x. I multiply each side through by y. So those guys cancel, right? And I end up getting a y over here. Here, let me do it this way. Right? And what's y? That, x to the 2x. So if I want to write this in terms of just x's, I've got it. Y prime equals all this stuff times y, which was e to the, what was it again? X to the 2x. Oh, whoops. Yeah, times x to the 2x. Done. Good? Okay. That's a good place to stop. Okay, do you guys have questions?